Hello, welcome to my presentation. My name's Roger Cracknell and I'm representing Concarway. Concarway is the European Refining Industries Organisation for Scientific Research and Development. My co-authors are from various other Concarway companies and also from Nexum. And I'd like to particularly thank Mike Barden, who's done most of the work in preparing this paper. So this is part of a wider study looking at fuels for advanced combustion systems. So you can characterize combustion systems effectively by a triangle with spark ignition, compression ignition, and homogeneous charge compression, HCCI, as the corners of that triangle. And effectively, all other embodiments of combustion systems fit within that triangle. Pure HCCI is more of a challenge to control. So people have often tried to adopt for compromise approaches, one of which is to use a spark to actually initiate the auto ignition so that most of the combustion is auto ignitive, but it's just the spark that provides the authority for the combustion phasing. Another approach is partially premixed combustion, in which, as the name suggests, the fuel air mixture is not homogeneous and the combustion phasing is actually controlled by the injection timing. And in that way, you can get the benefits of the HCCI essentially without losing the ability to be able to control the combustion. This taxonomy was developed by Bengt Johansson, and I find that it's particularly useful. If we look at what fuels we might want for partially premixed combustion, there are essentially a number of criteria that we might wish to apply. The first one is obviously whether it'll work in a PPC engine. The second one, which I think is often overlooked, is the availability of that fuel. Because if a fuel is not already available, you end up with a so-called chicken and egg problem, that there might be a reluctance to stock a fuel for which there's no demand, and there might be a reluctance for automotive manufacturers to manufacture vehicles which require a fuel which isn't easily available. The third criterion is looking at the diesel-gasoline demand ratio in European refineries. Currently, European refineries tend to be long on gasoline and short on diesel. And so anything that encourages the demand for gasoline is deemed to be useful. So if we evaluate possible fuels for partially premixed combustion against these criteria, first of all, if we look at diesel, yes, it'll certainly work in PPC engines, and it's clearly already available at retail stations, but what it won't do is to rebalance the diesel-gasoline demand ratio. It'll send it in completely the wrong direction. Gasoline, the topic of gasoline compression ignition is a big one in its own right, and I've actually got a separate paper based on some other work at this PFL conference, and it'd be great if you could take a look at that. Yeah, it's already available in retail stations clearly, and absolutely it will help to rebalance the diesel-gasoline demand ratio. A new lower cetane fuel, yes, it'll work certainly, but the problem with this, as I mentioned, is that it fails on the criterion of availability at retail stations, in that a new fuel would have to be sold, for which there would initially be very little market, and again there might be a reluctance to sell vehicles for which a new fuel would be required if it wasn't widely available. And whether it would help to rebalance the diesel-gasoline demand ratio would really depend on how that fuel was manufactured in terms of the refinery configuration. And finally, I'd like to consider blends of diesel and gasoline. Sometimes these are known as dieseline. And it's been shown that these can work in PPC engines. Certainly gasoline and diesel are available individually at retail stations, although some new infrastructure might be required to actually mix the two together. And whether it would help to rebalance the diesel-gasoline demand ratio would depend on the composition of the dieseling itself. Obviously, if it was mostly diesel, then it wouldn't do that, but if it was mostly gasoline, then it would. But there is another aspect of the practical application of it on a vehicle that I'd like to talk about, and that is the actual question of vapor space flammability, because it's known that if you mix gasoline and diesel together, you are more likely to get a flammable headspace in the tank. And that's really the topic of the rest of the presentation, to look at the vapor space flammability characteristics of dieseline mixtures. Fuel vapor pressure is a function of fuel volatility and ambient temperature. If you look at the extreme examples of diesel and gasoline, diesel, being not very volatile at all, tends to have a headspace that is too lean to burn, whereas by contrast, for gasoline, being much more volatile, tends to have a headspace that is too rich to burn. Now, if you add small amounts of gasoline to diesel of the order of 1% or less, it's known that that can result in a flammable headspace. And I think many of you will be familiar with the concept of diesel flash point. So adding gasoline to diesel will dramatically reduce the flash point. So really, for a practical gasoline diesel mixture to not be flammable, you generally have to exceed the rich limit. And so that's what we'll be focusing on for the rest of this presentation. So this is the fourth of 4 papers of previous work between Konkawi and Nexum looking at the topic of dieseline flammability. And in the first paper, we presented experimental measurements of flammability using a constant volume vessel. We found that under realistic scenarios, if you had around about 40% of gasoline in your mixture, you tended then to get a mixture for which the headspace was too rich to burn. You'd exceeded the upper flammability limit. In a subsequent paper, we developed a thermodynamic model to predict the rich limit as a function of fuel composition, ambient conditions, and other parameters such as fill level. And we also validated against the experimental data in the previous paper. And one thing we found is that because we'd taken literature values for flammability limits, which are based on ideal combustion conditions in a vertical flame tube, that our model was actually conservative, and the upper flammability limit temperatures tended to be around about 6 degrees higher than the experimental results that we'd seen in our constant volume chamber. In a subsequent piece of work, we applied this thermodynamic model to specific practical situations. And we found that the predicted UFL temperatures tended to be quite well correlated with DVPE, so that with the volatility of the fuel that was in the tank. Now, that's probably not so surprising, but we found that it was particularly clear if you didn't have any alcohol in the dieseling. It was a bit more of a challenge if there was ethanol or other alcohols in the fuels. Obviously, many gasolines themselves are E5s or E10s, so this would frequently be the case. And you could correlate the UFL temperatures well with DVP, but not as well as would be the case if you had just pure hydrocarbon blends. And we found that for a fixed percentage of ethanol in the blend, the ethanol always raised the UFL temperature, and the increase was always greater if you had a greater amount of ethanol. So the objective of this work is to actually utilize the relationship that we found between UFL temperature and DVPE, and actually produce some explicit formulae so that the UFL temperature can be easily quantified. And so this paper was really conceived as effectively a user guide for anyone to be able to come along and to be able to determine the UFL temperature based on these correlations that are presented in this work. So it was relatively straightforward for blends that don't contain ethanol, because you've essentially got this single relationship between the UFL temperature and DVPE. It is more complicated when you've got ethanol in the blend, and you can see that here's a dieseline with 10% ethanol with the red curve compared to the dieseline containing no ethanol, but for the black curve, and the presence of ethanol tends to shift the correlation to higher temperatures. Because ethanol has really two effects associated with it. The first of which is that ethanol tends to raise vapor pressure. And this is something that's really well known from fuel blending, the effect of ethanol on gasoline DVPE. And often, this is why there have often been DVPE waivers given to higher ethanol blends, because of that well-known effect. But also ethanol, because it has a different stoichiometric fuel-air ratio to hydrocarbons, actually has an intrinsically higher upper flammability limit temperature. And incorporating ethanol into a model that was actually the biggest challenge that we faced in developing these explicit formulas. So what we did was to kind of break down the problem. So in the red, if you see the DVP of the 10% ethanol blends, what we did was to, rather than plotting the full DVPE, we looked at the DVPE of the hydrocarbon components only and plotted those against the UFL temperature. And actually, in this way, we can help to break down the problem. And you can see that the impact of ethanol on DVPE can be seen to be most significant at low vapor pressure. And it's obviously less pronounced at the higher vapor pressure. So to summarize the approach that we've taken overall, we could have a single curve which can correlate the UFL temperature with DVP for any hydrocarbon-only dieseline blend, regardless of the specific hydrocarbon composition. But we recognize that if you've got ethanol, it can differ considerably from that hydrocarbon-only blend. So as we showed on the previous slide, if we plot the UFL of the ethanol blend against the DVP of the hydrocarbon-only portion of the blend rather than the DVP itself, then the curves differ from each other. But you get something that is much closer to the curve for hydrocarbon-only blends. And this provides a basis for developing our correlation. So we actually say that if you're determining the UFL temperature of a dieseline blend with ethanol, you start with looking at the upper flammability limit for the hydrocarbon portion only, and then you develop an adjustment term that depends on the ethanol percentage and the DVPE. And this can be expressed mathematically as follows, that F1 represents the correlating function of the curve for hydrocarbon-only blends, and the term involving F2 and F3 is that correction factor. Now, F1, F2, and F3 are just determined from a sixth order polynomial, where the arguments for F1, F2, and F3 are the DVP of the hydrocarbon only fraction, the percentage of ethanol, and again the DVP of the hydrocarbon only part of the respectively. Now the coefficients in the polynomial determined, and they're given here for a different number of cases. This is also given in the paper, so that you effectively just take these coefficients, you plug them into the polynomial based on whether you've got the DVP of the hydrocarbon only portion or the percentage ethanol, and then you are able to determine the terms that go into our explicit set of formulae. And we correlated this model against the full model, the full thermodynamic model. And you can see that really the agreement is quite good. So, as I mentioned earlier, the purpose of this paper is really just allowing a user who is interested in doing this to be able to determine the upper flammability limit temperature of a blend given a different set of input data. And so the paper gives a number of examples of how to use the correlations given a certain amount of input data. And I'm not going to go through all of the case studies, and I think that would be a little bit tedious. And I'm just going to go through the first case study, which is the simplest, where you've just got the DVPE of the hydrocarbon for an ethanol-free blend. So if we measure a DVPE of 44.6 kilopascals for an ethanol-free dieseline, if you look at the coefficients for the formulae, you can see that if ethanol is absent, then F2 is 0, and the UFL temperature becomes simply equal to F1. And if you take the coefficients for F1 and you plug in the argument, which is the DVPE of 44.6 kilopascals, then that allows you to calculate that the UFL temperature of the blend is minus 7.8 degrees C. So just to summarize this paper, we've developed explicit correlation equations to allow UFL temperatures to be estimated for dieseline blends with or without ethanol. And like the thermodynamic model on which it's based, the predictions are quite conservative in that they're based on flammability limits corresponding to optimum combustion conditions. The whole point of this was that the equations could be easily incorporated into models and spreadsheets to assess the UFL temperatures of a wide variety of dieseline formulations. So the idea is that they're effectively user-friendly, and the paper contains examples of using the equations under different circumstances and conditions. And I think more generally, a conclusion for the whole program is that it's important to raise the awareness of the issue of flammability characteristics when considering possible new fuels. And finally, in addition to acknowledging the authors themselves would like to acknowledge Konkawi member companies for permission to publish. And I'd like to also acknowledge Dylan, who's an intern at Shell, who meticulously went through all of the examples to make sure they were clear and correct, so that when you yourself go and look at the examples, you can be confident in them. And I'd like to say thank you to my audience for actually taking the time and trouble to listen to this presentation.